Hello, I'm Nick Feltz with the National Security Agency. I'm a researcher working on the Cyclone project, which is about securing data in use within cloud settings. Today we're looking at what trusted hardware can do to help us provide data at rest and eventually help protect data in use. So today's presentation, we're going to kind of look at what the cloud is. We're going to discuss what trusted hardware is, and we're really going to be addressing the securing data at scale in a cloud. This is a difficult problem, and solutions have varying degrees of protections and usability. We will be focusing our discussion on private clouds, which are going to be where you have instances where institutions are managing their own hardware and their own cloud. We're going to look at how we can give meaningful data security at scale in these environments. So even though we're going to be primarily discussing private clouds, I'm going to discuss the major cloud services and the offerings that they make. And I'm going to discuss what they make available throughout the slides for comparison. Mostly I'll be discussing Amazon, Microsoft, and Google Cloud Services. We base this on the Gartner Magic Quadrant, which put the three of them as kind of the three leading contenders for cloud providers. Each of them has their own key service that they offer to protect data, and each of them integrate this with their identity access management tools. So what is a cloud? Despite some misperceptions you see in some things maybe in media, it's not going to be this big mainframe. It's not going to be just a single supercomputer somewhere using. Clouds are traditionally defined as computing resources accessed remotely by multiple users across the internet. But for the sake of this discussion, I want you to think of clouds as being a set of individual computing nodes, so a bunch of individual computers in a rack, for example, in a single location. So in reality, clouds can have multiple locations and you will want to have redundancy. But when thinking about this design, imagine that you have a whole bunch of computing nodes and a computing platform all located within a single facility owned by one entity, but used by multiple entities across the internet. Clouds are known for offering a bunch of different services. Kind of initially, people discussed infrastructure as a service, platform as a service, and software as a service. We've started to see functions as a service and containers as a service, and the list of things that clouds can provide is going to continue to grow over time. For the sake of our discussion, we're going to be looking at software as a service, and specifically, we're going to be exploring distributed databases. Because when you're looking at protecting data at scale, a distributed database is a natural place to look at protecting that data. So trusted hardware, as I said, we're looking at how we can use that to protect data within cloud settings. There's a lot of different kinds of trusted hardware. HSMs, or hardware security modules, are cryptographic processors that have some tamper resistance built in. They host keys. They're very hardened devices. All of the major providers provide some access to HSMs as part of their key management system, but they can be very expensive for an individual or even a small institution to use with a private cloud. Trusted execution environments provide secure memory for program execution. It's important to note here that, kind of like with the cloud providers, we're not specifically talking about any one vendor or implementation of trusted execution environments. There are many different ones, such as Intel SGX or ARM Trust Zone. There have been a lot of research into the ways that these could be attacked or don't live up to all of their obligations, or maybe they are not powerful enough to do stuff. All of those things are not really the focus of this presentation. We are going to, in the next slide, discuss some of the assumptions we make about enclaves, and we are designing security tools and kind of discussing an approach to use these if these assumptions are met. So try not to focus on any one implementation if this is something you're familiar with, and think about the services that they can provide for the system. We refer to any instantiation of a specific environment and a program running in it as an enclave. So when I say enclave, I'm not talking specifically about, say, an SGX enclave. I am simply saying a program where all or part of it is running within trusted hardware, and specifically inside a trusted execution environment. And a hardware root of trust, such as trusted platform module allows the system to measure itself all the way from boot through execution. So you can measure things such as the BIOS and the master boot record, or programs that are that you want to execute. These devices are on almost every motherboard you can buy these days. They're on most machines. They're very ubiquitous, but they're not often used in cloud computing where the users don't have access to the hardware. So coming back to the assumptions for enclaves, this is an important slide because this provides the list of assumptions that we care about. Because we are assuming that we're running inside the context of a cloud, we assume that access to enclaves are going to be widely available to each computing node. In a perfect world, each node is going to have its own enclave and its own environment. Keys and data protected by the enclave should be encrypted until explicitly and intentionally output from the enclave. So nothing should leak unless it is specifically asked for and the enclave is designed to share that information. The enclave should not be accessible, modifiable, or corruptible without physical tampering of the chip. And they should provide some ability to attest to their state and the software that's running. So the software should be general purpose. There should be able to write software I need to run inside one of these, but there should be some method for me to verify that the software I'm running is actually the software I believe is running. So if we can meet these assumptions, we can use these to provide some real security, as we're going to see within a cloud environment. So from the large services, all three offer access to HSMs, and that is because HSMs can be expensive, these services can be a cheaper way to use them. It is unclear that they know what to do with some of the other trusted hardware offerings. I think the market right now is kind of exploring how to use the other trusted hardware. Azure offers SGX access. Google's developing Azilo, which I believe is designed for using Intel SGX. And Amazon offers Nitro for EC2. Each of these is coming along. The offerings are becoming stronger, but it's still kind of a new market. They're trying to figure out how can we best leverage these tools to protect cloud environments. So, kind of framing the problem, I got a couple examples here from a couple experts with different companies and things that they've observed. The first question was really brought up by Dr. Yasir Nawaz, who's the executive director of cybersecurity at JP Morgan. He gave a keynote at the ACM CCS Cloud Workshop in 2019, where he asked questions about how was encryption useful. He pointed out that it's very difficult to encrypt beyond the storage layer. That offering meaningful and real encryption that actually protects data is a difficult problem, and how can we do that? Encryption should do more than it currently does, and he pointed out that it does not do much more beyond the default access controls. He observed that it was very useful for deleting data, but he said, with something this powerful, we should be doing something more with it. And our second bullet came from, this idea came from Dr. Mark Russinovich, a CTO for Microsoft Azure, who claimed that it was the goal of Microsoft Azure to prevent anyone from being able to demand a data set from Azure. They wanted to design a system, and their goal was to build a system so that anybody demanding user data would be unable to retrieve it. The system admins would not be capable of retrieving that data without the informed consent of the data owner. So the premise and the problem we're trying to solve is meaningful encryption at scale is hard. We see a case where JP Morgan and Microsoft both were looking to solve this problem and saying, hey, we need to find ways to make this a reality. Dr. Nawaz observes that it is easy to implement secure solutions for specific problems, but these approaches break down in a wider ecosystem. And he actively questioned the value of encryption beyond a compliance check. So I would say that the real emphasis of this problem is on the word meaningful. And by meaningful, we mean that it protects the data confidentiality and it gives control of that data to the owner, who can share or restrict access as desired. This is difficult to do for a variety of reasons you see here, but managing keys is really, really hard. HSMs are a potential answer and are really good for some problems, but a lot of the major providers don't recommend you use them to protect your distributed databases because the HSMs become a bottleneck. They're not meant to perform at that kind of scale. Second, and I think this is kind of of equal importance for a lot of people, the data owners have no implicit reason to trust system administrators they don't know. The systems in the cloud are being controlled and managed remotely by individuals that they don't know, that they've never met, that aren't on their payroll. And so building that trust can be difficult. So if we can remove the need for that trust, data owners can be more comfortable with what they're sharing. And right now, legal protections exist to, if somebody's at fault, there's a way to litigate and go through that if something does get leaked or a breach does happen. And I think that sometimes these protections can kind of make security break down to a series of checkboxes where people are just trying to say, yes, I met this compliance, I did all the things I was supposed to, and people lose sight of the real goals. And security should not just be a checkbox. It should be about making the adversary's job more difficult. And we think that trusted hardware can play a role in protecting data at scale because trusted execution environments offer the opportunity to distribute that workload of protecting the data to the individual nodes. And this allows us to move the processing to the data, which is what clouds do anyways. The idea is moving data is very expensive. Moving execution to data is much cheaper. Well, let's move those protections to the same level. And, can use this to alleviate some of the bottleneck that things like HSMs can create. So looking at private clouds, many smaller companies use cloud services provided by major vendors, but many places still manage their own hardware. These cloud systems are not designed to the same scale. They don't quite solve some of the same problems, and the underlying hardware and access to it can be different because they own, they support, and they manage their own infrastructure. So the hardware for the private clouds is more likely to be off-the-shelf commodity hardware and is more likely to include things like TPM and Ts potentially on the nodes that are in the rack. But there may not always be support for expensive modules like HSMs or dedicated key servers. So at the end of the day, even though the scale is a little bit different, the services are largely the same, but tailor fit for their specific needs. But they're likely to provide things such as a distributed database for the enterprise system to use, and they're going to provide some processing power to use alongside that. So we're going to focus our discussion on how you could use some of the offerings that these have, some of the hardware they have. A lot of these ideas would potentially translate to larger cloud installations, and maybe you could look at how to incorporate HSMs, and we're going to discuss some of those ideas later. But it's a lot easier, I think, to think about these in terms of familiar hardware that's going to be accessible to more institutions. So before you can get to data in use encryption, we really need to look at how you can do data at rest encryption at scale. That's really where some of the prior discussion was about how useful is encryption. And object level encryption is a service offered by major vendors. You see things like being able to encrypt the AWS S3 buckets. And these provide some limited value. They resonate really strongly of that mentality, though, of I am in compliance. I can delete the data easily. I've done all this stuff. But what is the real value of that encryption? What are you really protecting? What is the threat model you're concerned about? So by looking instead of at the individual object there and thinking about this from the distributed database layer, we find a really interesting question and a really interesting place to look at how you protect data. These database services are often run alongside other cloud services. So even in installations that are going to use a lot of virtual machines and services are going to have a distributed database that the people can also use. And you're going to run jobs like MapReduce or any of these big cloud analytics, MapReduce just being one example, on this kind of data. And what's really nice is this data can be very heterogeneous. Some of it can be sensitive, some of it may not be sensitive. It's going to be structured differently. You have a wide variety of different needs all within one database. And there's a lot of options for where and how to protect that data. As you move the encryption higher up the application stack from the local disk into the database, we can move the control of that encryption closer to the data owner. So a data owner who has a table in a specific database might be able to configure the encryption for that table, whereas if you're looking at local hard disk encryption, they have very little control and their data is going to be encrypted much the same as everybody else's. I think what's interesting with distributed databases is you have some opportunity to provide some of these automatic tools, some of these flip a switch, and you can provide meaningful encryption that's not terribly difficult to turn on, but offers more protection than just a compliance check. And this will always boil down to, again, the issue of key management. If you're going to allow the data owner to control the encryption and how they're protecting their data, they're also going to need to have some control over the key, and they need to understand the pros and cons of how to manage that. So there's the crux of this slide is really highlighting that very uncomfortable dichotomy. If a data owner manages their own encryption and encrypts and decrypts data outside of the cloud entirely and just says, I'm using the cloud as a storage venue, that's great, and for some applications that's absolutely the right way to go. The downside to that is they lose the ability to leverage the processing power of the cloud. They do not have the capability to run these big jobs because the data is encrypted. On the other hand, if they pass the key to the cloud whenever they need to run a job, they have to manage the key themselves. They have to make sure the key can get there, but they can minimize the exposure and only have decrypted data while these things are active, but it's still exposed to the cloud, so there is some risk. And then in the case where they're willing to give the key to the cloud to manage the store for them, their job for key management becomes much easier because they put that responsibility on the cloud. However, they maximize their exposure because they're also using the cloud to perform the encryption and decryption, and they've handed over that access. So their risk of exposure is the greatest, but their processing power is also the greatest. And so there's kind of this uncomfortable you figuring out the right way to go. Where's the happy balance? And so thinking about key management, we've discussed who stores, who controls the key, and the management can be difficult and costly. HSMs are the ideal place to store a key, but they're just too slow to use with large applications where you need to call and use a key over and over and over for something like a distributed database, and they're not always available with your private clouds. Storing the keys inside a local or distributed file system allows for maximum flexibility. It's very easy to use them. It's very easy to make them available, but you lose that control. They are more available. A key server can be used, but they can be very costly, and they create the same bottleneck that HSMs use. So what we are interested in looking at is, can we use any of these other options? Can we look at the use of other trusted hardware to solve some of these problems? And TPMs, as I mentioned earlier, they offer the ability to measure system state and they can protect data by only decrypting data or keys if measurements are successful. They can measure the BIOS and the master boot record, and they can look at the software you actually want to execute. You could measure the database software itself to make sure you're executing only on the version you want the key to be used with. That can create some difficulty when updating software, but those things can be accounted for so that you know that you're always executing and only giving the key to a version of the software that you trust. Ts offer the opportunity to additionally do some trusted compute, which minimizes the exposure of secrets to other users and to system administrators. Azure has a really cool program where they do some AI inside a trusted enclave in the cloud, and I believe they've got a blog and some videos, and some of the core, maybe all of it now, is open source for how they do this, where they take two different hospital data sets and they're able to do some machine learning and output the results without either hospital having to share its information with the other, which is really cool and really awesome. And I think that would be a great example of the killer app that I hear people asking for at these security conferences, where they're advocating that's really what Ts need, this killer app. But I don't see a lot of products going that way. I don't see a lot of offerings where this is just natively a part of the product, because at the end of the day, security is never really the shiny part of the tool. Security is something we want our tools to support, but is not necessarily the goal itself. And so I think thinking of this in terms of a killer app is maybe the wrong way to approach it. And instead, we want to think about how can we explore integrating trusted execution environments as part of the architectural design in the cloud so that their use can be effectively toggled on or off to protect data from users and administrators, and see if we can do this without performance becoming a major constraint. Because if HSMs and key servers already provide a lot of that functionality, but create that bottleneck. Right now, when looking for the best you can do, there's a natural question of homomorphic encryption versus trusted execution environments, and trusted hardware in general. Unfortunately, while homomorphic encryption might be suitable for some problems, it's still an active research area and may not scale to the demands of cloud computing. And, T's and other trusted hardware are all kind of new, so they're still being developed as well. But I think in the meantime, we'll see where both products go. But right now, I think trusted hardware gives you some real protection that could be used today and are a practical option towards looking at data in use protections. And I think that you can start this and you can start using their offerings by, instead of thinking in terms of just data in use, looking at key in use protection at scale. Often in security, we kind of take this all or nothing design and we take this approach of everything is really totally secure or it's not. And I think when thinking of solutions to problems, it's okay to start that way. But security's real purpose is to make it harder for the adversary. It is to make their job more difficult. If you can protect keys in use at scale, you may not be protecting all of the data, but you're definitely raising that bar and making it harder. So it offers some of these real protections. By protecting the keys, it never exposing them in plain text to the system, and it helps establish the practices and the tools and the expertise and the knowledge needed to incorporate later tools. You can start building those principles into your clouds today, and protect your keys, knowing that as hardware becomes more powerful, as more software is made available, you can start transitioning towards data in use solutions as well. Ideally, keys in use system will not take advantage only of the trusted hardware, but it will also take advantage of the identity and access management features, so that it should be something that's easy to enable and toggle, and the data owner should have a lot of control over who and what can access their keys. Again, while this approach can leave the data exposed, it protects the keys, and it can have a much smaller performance hit than using some of your standard hardware such as HSMs. So here we've got kind of a bird's eye view of how we're going to look at data and use protection. So before I get started, I kind of want to make clear what you're looking at here. On the right side, you have a user terminal where you have somebody, it could be a data owner, it could be a data user, who's going to be making a request where they want to make some query from the database. On the left side of that line, where you have the enclave boxes, all of those boxes are going to be, once that request has been forwarded to a specific node. So we're kind of waving our hands at the process of getting across the internet to that node, but this is going to be a specific node running on one machine inside of a cloud. So you could have a request that processes data that takes place on multiple nodes and have several of these running in parallel. But for thinking through what that process looks like, we're going to look at just one node within the cloud that is handling the request. And something else that I may bring up again later is the enclaves are logically separated here. It is possible that you would implement them as separate enclaves. It's also possible that they would all be one enclave. But it's very easy to think about this process in terms of what is the enclave doing logically separately. Again, you could implement it that way. So because the systems, and the reason that we're looking at the node specifically is because we want to move that compute to the data. So keep in mind, this is one node. This is not something magically running next to or aside the cloud. This is every node should ideally be able to do this. So the request comes in, it eventually makes it to the analytic enclave, which says I need access to some data. And it is going to query the database and say, hey, I need access to these resources. You can think about the distributed database as, maybe an encrypted phone book. And the analytic engine might say, hey, I need all businesses in this section about this thing, whatever it is. And the database knows something about how it's organized, even if the contents themselves are encrypted. So we're going to take a second, stop looking at the whole system, and look at just kind of what that database process itself looks like. Each distributed database implementation sorts and stores the data in ways that are optimized for its intended uses. But there are some general structures that most of them follow. So many of them, for example, will store files on a distributed file system, and they will encrypt data at that level. They will encrypt it within the files, and they will have these file encryption keys that are potentially protected by a hierarchy of other keys. But for the sake of this example, we're going to think of it as just having one key encryption key that protects the entire distributed database. And so there's a key encryption key that is used to wrap and unwrap these file encryption keys. And these file encryption keys are stored encrypted as metadata about the file. And sometimes that's stored in the file, sometimes that's stored externally. Each database kind of handles that a little differently. So when a query comes in, the distributed database is asked for some data, and the database is going to retrieve the file it needs and pass some contents to both a data broker and a key broker. Now, as I said before, these brokers could be, these enclaves could all be one enclave in one program. They actually could also be nested into the database. The database could have part of its software running inside the enclave itself. Again, the separation is just to kind of logically think about how the data flows, but enclaves support the idea that only part of program execution happens in there. So it is entirely possible that you have a data broker enclave and a key broker enclave that are part of that distributed database software. So however that is organized, the database will hand the different components to the key broker and to the data broker. It's going to give the data to the data broker to decrypt and the key information to the key broker enclave. The key broker enclave will unwrap the file encryption key, which was encrypted in the database, has only been unwrapped within trusted hardware, so it's never been exposed in plain text to the system, and then it's going to pass that key from one protected environment to another. So it remains encrypted in memory the whole time. Once the data broker enclave has that key, it is able to then decrypt the data. And now the data is still inside protected memory, so it's still inside protected execution. And it's going to pass that to an analytic enclave, which in this example is also running inside a protected environment for processing. So the data that was encrypted on disk was encrypted until it went into the enclave. The keys were encrypted on disk and encrypted until they went into an enclave. All the processing happens within an enclave, and at no point do you have data anywhere on the system that is in plain text and not in protected memory. So that is something that is a really great goal, and I'd love to see that happening, but it is a really big ask to have these analytic engines doing this at scale today. You would have to have every analytic engine, everything that's processing, doing these big jobs on data, be able to execute a large chunk of their toolbox within the enclave. So instead of thinking about the analytic software protecting that, let's think about how can we just focus on protecting the keys that are being used, knowing that we're going to end up putting the data out through the analytic software. So you'll notice here that the analytic software is no longer in an enclave. Once the data goes into it, it is no longer in protected hardware at this point. So in this case, the distributed database is working directly with the key broker, and the keys, the key encryption key is protected somewhere by trusted hardware. we're not going to be looking at specific implementations and how exactly that would play out. Each system is going to be a little bit different, but the trusted hardware options could include HSMs, TPMs, and key servers, and they're not mutually exclusive. You could have the node use a TPM to protect its boot process. When it boots up, it unlocks some material, a certificate maybe, that it uses to connect to a remote key server that has an HSM that's storing the keys. So these are not mutually exclusive. You can use what is available, and I think that is how you would be best served. In this case, the distributed database is going to have some encrypted data. Again, it may do the decryption itself. It may not pass the encrypted data to the analytics. I'm trying to show the logical separation here of where the data is going and what is exposed where. So the decryption could very well happen in the distributed database. But for the logical discussion here, the encrypted data goes out in the analytics software, and the key ID, the KEK ID, and the wrapped file encryption keys are passed to the key broker. The key broker sends off the key encryption key identifier and potentially some other authentication or authorization material, depending on how you've got that set up. If it's a key server, if it's an HSM running locally, whatever that looks like, it passes what is necessary and the key encryption key identifier. If everything goes well, it gets back a key encryption key, but now the enclave can cache that key. So instead of creating a bottleneck with an HSM where we are repeatedly asking it for a key to use a distributed database, we can have the database first query for that key, load it from an HSM, and then hold it in trusted execution for future use, so that we have effectively eliminated that bottleneck, but we're still protecting that key in trusted hardware so that it is never exposed. And this is kind of the idea of using keys in use. So now we've protected that key encryption key that protects the whole database from being exposed to another user or to a system administrator. And in this case, the file encryption key comes out of the key broker, and that file encryption key is used to decrypt the data. If we had a data broker as well, you could pass the key information from the key broker into the data broker, and you could pass the encrypted data into the data broker and let that do the decryption, so that you also never expose the file encryption key. So in that case, you would be protecting the key encryption key and the file encryption key, but the data still comes out, and you would have real protections. Nobody can come in later and read your data. They only have access to it while it's actively being processed. So going back to the bird's eye view, we have some idea of what the querying the database looks like and how we might protect the keys in use. So the database is going to send the information, as we discussed, to both the key broker enclave and the data broker enclave. The key broker enclave sends back the key material, which sends the encrypted data to the analytic enclave, which, depending on what questions that analytic enclave is answering, might not send back any data at all. It may just answer a question about the data. And so if you could leverage trusted hardware to accomplish that goal, you never have to expose your encrypted data at any point in the processing. But again, the analytic enclave, doing that is very difficult. That is a big lift. There's a lot of tools that are going to require a lot of effort to make that happen. But I think that moving back and saying, okay, how can we protect just the keys? How can we use HSMs and, cache these keys locally inside a trusted execution environment for use in things like distributed databases, offers a more practical solution and gives you meaningful protections, because that key is not actually being exposed to the rest of the system, to the rest of the environment, or to anybody who gets on that machine with root access. I also want to reinforce, we were talking in this context about a specific node on a system. There's going to be a lot of nodes in a cloud. Each one of them should have their own set of enclaves doing this. So in a world where you have one distributed database, looking at private clouds, this could be a reality. You have one distributed database and you have one key encryption key that's protecting all the files. whenever the system boots up and it does its first query or its first write, and it has to get access to that key encryption key, it could go off to a key server, to an HSM, to a TPM, some combination of all of those, retrieve that, and then for all future queries, it already has it locally saved in trusted hardware ready to use. So you have effectively eliminated the continual use of the bottleneck and protected the key while it's being used. I think that it provides some real meaningful and powerful protections, and it is a step in the right direction. Once that is in place, it becomes easier to think about, well, how can I protect the file encryption keys, as we discussed? And okay, well, now that I can do that, how can I actually protect the data? Maybe I can protect it in some analytics and not others. And you have kind of the pathway, the hardware, the expertise, the tools in place so that all of these ideas are familiar and comfortable. So I think that if you are currently looking at trying to put protections in your own local private cloud, these are things to really consider using and see what's available, and see what you can do to implement these ideas. So the key takeaways, trusted hardware has the potential to provide real and meaningful protections to data in use and data at rest. And the goal is to make an adversary's job harder, this is something that the trusted hardware can currently provide today. Protecting keys in use requires less powerful enclaves than doing data in use. So you don't have to say, I've got an all or nothing solution. You can start by focusing on just the keys. And as I said, it paves the way. You develop the expertise, the knowledge, the ability. You'll have some tools to build off of. You're putting that framework in place and making it part of the architecture so that you're no longer looking for what is the killer app, what is the really cool thing I can do with it, but instead saying, can I design a system so that a data owner who really wants to protect their data can flip a switch and say, protect these keys, always in trusted hardware, and it just happens for them. And I think this will become more and more practical, and the opportunities to really leverage these ideas will continue to grow as secure enclaves become more powerful and more readily available. We have some current work that we've been doing on this. We have a couple GitHub repositories that anybody's welcome to come by, contribute to, comment on, and talk with us. And thank you for your time.